saying that like it's a conscious decision, which I know
it's
not.
so conscious. Yeah, water is like, nope, not enough yet. You got to hang on. Wait. Nope, we still got a few more of those drops coming. All right, 3 more. All right, now you can go. Yeah. Now you can drop. All right, perfect. Hi, I'm Ryan. I'm a science teacher.
I'm Cheryl, and I slept through science.
Each episode will tackle a science question you may have learned in school, but can't quite remember or fully explain.
And I'll take the risk of asking the dumb questions so that we can all understand the science we slept through.
The bell has rung. Let's get started. Welcome to lesson 57. We are still answering listener questions this week. Cheryl, whose question are we answering today?
Well, Ryan, last week we answered Jane's question, and we had talked about, she's a friend of ours, and how she is a homeschool mom and has 2 kids, and sometimes our podcasts are a part of their lessons. So her kids each asked a question. So her son, Colin, who you and I were just trying to figure out because we're feeling really old right now, trying to figure out, like, he's a teenager, but we don't know, like, time is passing us by very quickly, and apparently he's no longer a baby.
COVID makes that hard too.
Yeah, sure. Okay, we'll say that. Anyway, Colin, who's one of our listeners, he has a question this week, and it is there an explanation for the rhythm of a dripping faucet?
Yes.
Great.
Done.
Cool.
That was easy.
Solved. Wow.
Oh, sorry. I didn't let you do the pre-assessment. I just answered.
Yeah, I guess we could say what. So if there is an explanation, well, what is it?
Okay. Okay. You're not going to let me off that easy, huh?
No, I'm sure not.
Okay. Well, let's move into the pre-assessment then. What do you think might explain the rhythm of a dripping faucet? Well, let's even go back. What is the rhythm of a dripping faucet?
Well, I mean, it probably depends on the faucet, and I have not heard Colin's faucet at his home.
Mm-hmm.
But I do have a dripping faucet at my home, and sometimes it feels like it is just very steady.
Okay.
Like, honestly, you could, like, it's like a metronome. I mean, you could just like use it to keep a beat. And then I think sometimes it still keeps a beat, but it's like a dut 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 dut. You know, it's like a slow, quick, or things like that. So, but either way, there is a rhythm that they take that's pretty steady.
Okay. What do you think might cause that rhythm?
Well, water's leaking.
Okay.
I mean, I would just guess that, like, it's a leak, but it's a slow leak, right? It's not just like water's like pouring out of the faucet, but it's enough that drops are coming out of it. And so I would think that as the water like gets to the edge of where it is, it needs enough to become a water droplet.
Okay.
Like, that's
what do you mean
maybe
by that?
heavy enough.
Okay.
Well, like, I don't know if there's like a standard size of a droplet. Like, even when you cook, I mean, okay, cooking's funny because it lasts for like a pinch of things, and you're like, well, a pinch, that's not really a standard size.
Nope.
I don't think that works in science so well to do a pinch of something.
No.
But okay, Lou and I, maybe not cooking, but when I make my own hand lotion, and I use essential oils to make it scented, and I'll put like 15 drops of this essential oil. So like when I'm using my little dropper and getting a drop in it, is a drop of liquid like a standard size? Is it always the same size? Or does it, like, I would think water would need to accumulate enough to form a drop. And if there's less water than that, then maybe it's not. I don't know if it's not heavy enough to fall. If it's just like less, it is just going to be like, going back to the faucet, like a tiny bit of wetness. on the
Okay.
edge of the faucet versus like enough water comes and then it can like it goes all together and forms into a droplet and then falls. So
Okay.
but I don't know like does it do that? Obviously it does it at the same rate, which that part makes sense to me that it's the same rate because however much the leak is or like it hasn't changed, and so it feels like it's just going to keep coming out at the same rate. But I'm curious about the water droplet now.
Okay. What do you think is holding the water to the faucet? Because you said if it's heavy enough, but why would it not just always fall?
Oh my gosh, I have no idea. I can totally picture what you're saying because it happens all the time. I mean, even after it rains, like water can stay on a window a little bit or, all sorts of surfaces can stay wet even though. So like, does water want to stay together? Like water wants to stay with water. And so this isn't quite your question, but I'm also picturing like on a window that when it is wet, that you see actual like droplets as opposed to like the window. If you took like your hand and wiped the water across it, then it might spread out more. But even when you do that, it like doesn't spread out perfectly. It's like in little drops or in little pieces. So it feels like water wants to stay with itself.
Okay.
Instead of just spreading out. Is that because it's a liquid? Like if it were a gas, it just spread out. So because it's a liquid, it wants to stay with the other molecules. I know it's made of molecules, but like, is it a molecular thing? But then as far as why, so then like, does it just want to stay where it is until it's heavy enough that gravity pulls it down? And before that, it just wants to stay with its buddies.
It wants to stay with its buddies?
Yeah. Now I'm just picturing your little Mickey Mouse molecules too.
Sticking to their buddies?
Yes. But that's weird because that's defying gravity. Whoa. That's odd. Yeah, why wouldn't it just instantly fall out of the faucet the second it's there?
Yeah.
In tiny, tiny particles or molecules or whatever.
Or just like a constant stream that's just really, really thin.
Yeah. It waits until there's enough of it.
It does.
I'm saying that like it's a conscious decision, which I know it's not.
So conscious. Yeah, water is like, nope, not enough yet. You got to hang on. Wait. Nope, we still got a few more of those drops coming. All right, 3 more. All right, now you can go. Yeah. Now you can drop. All right, perfect.
That's what it seems like, though.
It is
like
kind of what it seems like.
the guy at the top of the water slide who like won't let you go down until the next one's clear or whatever. Yep.
Yeah. Okay. Well, Cheryl, are you ready to get into the full explanation?
As long as it involves those little Mickey Mouse molecules, then yes.
You mean these?
Yay! Yes. Oh my gosh, everybody needs to join us on YouTube so that you can see these cute little molecules. Are there magnets in them? How are those like?
These particular ones, yes, there are magnets that hold them together. These are actually, these are from a YouTuber that I've followed for years that does some really cool things. He made them, they're called snatoms.
Like snap and atoms? Is that what we're?
Yes.
Okay.
And actually these are the micro snatoms. So they're the smaller ones. I have another set at school that are the normal sized ones and they're significantly larger. So.
Oh, that's probably nice in front of a classroom as opposed to a camera. Here.
Exactly. Yes. Nice. But no, they're magnetic and that's how they stick together.
He made them? Like that's like his product? That's so cool.
Yeah. Yeah. I'll make sure that I link to his store. It's Veritasium, if anyone's familiar with that YouTube channel. It does great stuff. But I'll link to his store. So if people want to buy some, they can.
So fun.
They are fun.
Okay.
Anyway, so what do these represent again, Cheryl?
Water molecules.
Water
H2O.
molecules. H2O. And just as a reminder and to describe for those who can't see right now, what exactly is one molecule? What does it look like?
Well, it is a larger single circle, sphere, I guess you could say, that represents, it's 1 hydrogen and 2 oxygen.
Well, what's the formula?
Well, H2O, but I always forget if the number means that it's applied to the first one or the second one.
Like the first one.
Oh, okay. So it's the big one is the oxygen.
The big one is the oxygen.
The big one.
It's kind of a reddish orange color.
2 smaller spheres, like Mickey Mouse ears.
They're at an angle like Mickey Mouse ears.
That are they're 2 hydrogens.
Yep. And what color are those?
They're white.
White. And you're not always going to see those colors with every molecular model, but these are the common colors that are used for hydrogen and oxygen.
Oh, okay.
Yeah. And there, again, it's a model, so it doesn't have to be, there's no physical reason that they would have to be that, but it is helpful to kind of standardize those things so that when you're doing different models made by different people, they have similar colors and you can recognize what they are. So we've talked about these before. And what are the cool things about water? There's a ton of cool things about water. But what are the things that you mentioned that is actually true and is factoring into this is water molecules like to stick to each other. And we won't go into all the reasons why, but I think I've referenced this before, but I don't remember which lesson it would have been. But because of the way that atoms bond to each other to make a molecule, they are, in this particular case, they are sharing electrons. And you've heard of electrons before? Okay, and electrons are part of what make up an atom, and they have a negative charge. So every electron has a -1 charge. And because of the way oxygen and hydrogen interact with each other, those electrons spend a little bit more time around the oxygen than they do around the 2 hydrogens, which means the oxygen is a little bit more negative than the hydrogens are.
Okay.
Does that sort of make sense?
Yeah.
Okay. Well, that also means that then the hydrogens are slightly more positive than the oxygen, which means when you have multiple water molecules next to each other, the slightly negative parts attract the slightly positive parts, and they sort of kind of stick to each other, which means that the hydrogens kind of stick to the oxygen of the next door molecule. Is that making sense?
Yeah, and I don't know, because we've talked about water molecules, like when we talked about dissolving, and we've talked about boiling water as well. So I feel like kind of amongst those lessons, we haven't talked about exactly that, but yeah, like
right. Okay.
That makes sense. Yeah.
And they all kind of stick to each other. And it's so common, we call it a hydrogen bond.
Oh, I've heard of that.
Yeah, it's not a bond in the same sense that like these hydrogens are bonded to the oxygen to make water. It's not as strong as that, but it's strong enough that they can sort of kind of stick to each other. It's still liquid, right? If it's liquid water, which means they're still going to slide around, but they're going to be attracted to each other. And that attraction is the most noticeable on the surface of the substance, because on the surface, you only have water molecules below that very top layer, because it's air above the surface of the water.
By definition.
Exactly.
Yeah.
Which means there's only that attraction between molecules pulling down on that very top layer of the water.
Oh, that's why you're saying that. Okay. Yeah.
So it means instead of being pulled in all directions by all the water molecules, they're pulled a little bit more strongly down and across to each other, but there isn't anything pulling them up anymore. And so it kind of creates this sort of stickiness to each other on that very outer edge. Actually, over Christmas, my nephews were in town, and with one of them is into science, and I had him do this. I don't know if you've ever done this before. Have you ever used like an eyedropper to put drops of water on the top of a penny?
No.
Oh, you want a little experiment to try, Cheryl? How
Specifically
many?
a penny?
I mean, it doesn't have to be a penny, but you can see it the most on a penny.
Okay. Okay.
Like, how many water drops can you get on the top of a penny?
Oh, does it get like a big dome?
It gets a big dome. Yeah. Have you
Oh
ever done
my
it like in a
gosh.
glass where you like fill it all the way to the top and then you can go just a little bit more and it kind of domes along the top?
Yep.
Right?
Yeah.
That's all the same thing. That's that surface tension, or you also call it cohesion. It's sticking to itself. Okay. And water does that. This is not related to water, but I want to show you anyway because I think it's cool. I happen to have a sample of my favorite element from the periodic table. Do you know what my favorite element is?
I mean, I would guess mercury.
Mm-hmm.
Okay.
Yeah. Why would you guess mercury?
Because you've talked about it before. I don't even know on or off the podcast.
Okay.
I'm not sure.
Yeah. No, mercury is definitely my favorite element. And it's because it's the only metal that is a liquid at room temperature. And it's incredibly dense and incredibly cool. And here I've got a little vial with it. I'm going to turn off one of my lights so it doesn't reflect quite as much. But if you look at the top, I don't know how well this is going to do it. Do you see that there's a dome along the top of the mercury also?
Yes.
Okay. Because you can sort of see like, oh, don't do that. Focus on this. Oh, it unfocused. Well, there's a line right here. That's actually the surface. And then that part that's extra shiny at the top, that is actually it's called the meniscus, but it like is bulging up. It's that same sort of a thing. It's just that mercury does it way more than water does. So it's very, very cool. And it's just a very cool liquid metal. Like it doesn't even like splash. It actually holds onto itself so much more. Remember when you talked about if you have water like on a window or glass, you could smear it and it kind of beads up, but it still stays on the glass.
Yes.
Mercury's cohesion or surface tension is so strong that even if I like splash it around, and this is in a glass vial, you still don't hardly get like any drops on the sides. Yeah, it's just like
instantly it goes all back together.
Yep, because
it's like water would like slowly drip down the side if you splash.
But mercury is both extra heavy; it's really dense, and then also its stickiness to itself is so strong that it just pulls itself right back down again. It's very, very cool.
So, if in Colin's bathroom he had a mercury leak, here I'm gonna make a hypothesis. Ryan.
Oh, ooh, yes.
If he had a mercury leak instead of a water leak in his faucet, I think there would be, and if it was coming out at the same rate, I think there would be more time in between the mercury drops instead of the water drops.
Okay, and why would you make that prediction?
Well, I'm guessing where you're going with this whole liquid molecules sticking together is that that force is stronger than gravity until it's a big enough amount of water that then gravity wins. Yep. And so then I think that if the force in mercury is even stronger, that then it would wait until it's like even bigger droplets before gravity would win and take over. Yeah. Although mercury's heavier.
Yep.
I wish we could put mercury in Colin's pipes so that we could do this experiment. Yeah. But I don't think his mom would like that very much.
Probably not so much. I'm sure that there is a way to experiment that without actually putting it in pipes. Actually, I'll bet what you could do is if you just got the same eyedropper and you put an eyedropper with water and then that same eyedropper with mercury in it and just see how big it gets before it falls. I'll bet that would give us a good approximation for it. But yeah, mercury can be toxic. So we're not going to put it in a place where we could potentially inhale it or drink it or anything like that. Okay. But your thinking is exactly right. The only thing that I would say is it is so dense and so much more dense and so much heavier than water. Would that overcome more quickly and actually cause it to drip faster?
Interesting.
But I don't know how the two of those compare to each other. But you're exactly right. That's what's holding the water drop up in the faucet before it actually falls. That thing that kind of, you were like, wait, I don't know how that works.
Yeah.
Right? So that's what it is. And so all it is a little bit more water coming. And as you already said, it's coming at a steady rate. It's very, very slow, but it's a steady rate, which is why the drop slowly grows. And once it's big enough so that there's enough mass there, it's heavy enough that the force of gravity pulling it down is stronger than the force of all of those water molecules and their surface tension pulling on itself and pulling it up, then it actually falls the rest of the way down, and then it's a drip.
So it goes from a drop to a drip?
Yes. I feel like that's like a pinch.
Yeah.
So yeah, I mean, I think that's most of it. Are there any outstanding questions that you still have based on the explanation there?
So then one of the questions I'd asked you was if a droplet of water is a standard size.
Right. You had asked that. It depends on how standard you want standard to be.
So I think what you're saying then is that like pretty similar, but like if you get to like exact measurements, you're not going to get like perfect the same size, but like pretty close.
From our eyes, they're going to look really, really similar. Now, it is going to vary, especially from a faucet. There's a couple of things that'll cause it to vary. One is exactly what's in your water, because the water isn't just water molecules, H2O. There's minerals and other things that are dissolved in the water that all affect water's ability to do that. You know, if you have hard water or soft water or well water or, you know, whatever it is, there's the actual liquid itself isn't just pure water. So that's a factor. Also, in addition to cohesion, where water sticks to itself, water also has a property called adhesion, where it sticks to other things, like glass, for example, like you had talked about, where it like sits on the window, because there's a little bit where it can stick to other things. And depending on what your faucet is made of and what the hole, like the opening, what its shape is, that can also kind of affect how much the water is able to stick to something else and stick to itself. And like, where is that? How big does that is that opening? All of those pieces, kind of going back to the lesson when we talked about the straw. And remember the straw being able to hold some of the water in. There are times if you, we talked about the trick where you take like a note card or something and you put it on a cup with water and you flip it upside down and the card will hold, the air pressure will keep it up. You can actually do something similar if you have small enough holes. Like if you were to take like a screen material, you know, like you would have like in the screen, like on your window, and you do the card again, but now you've got this screen and you flip it upside down and then you take the card off and it'll drip a little bit. But as long as the holes are small enough, the water molecules are able to hold on to each other enough in between those spaces. The spaces are so small that it can't actually pull down. So you can actually hold on to itself almost as if there's a surface there also. So water can do a lot of really cool things, which is why, is there a standard drop size? Well, yes, but also no.
Yeah. Interesting. That's really cool.
Yeah. I mean, I think so. I think water is one of the most fascinating substances out there. And I mean, if you think about it, as far as we know, water is required for life. And part of the reason for that is because it has all of these very, very unique properties that can do so much in a unique way to most other substances. It's very cool. You know what's next, Cheryl?
Oh gosh, I was gonna try to make some like clever thing about like the molecules building up and then it's a drip and that's somehow a pop quiz, but even now that I say it and it's not a clever, it makes no sense. The quiz is
she says with enthusiasm.
What we're doing. I don't know. Can we have the Mickey Mouse molecules during the quiz? Is that a
Sure.
possibility?
Yeah.
Are they
here you go.
incorporated?
Does it make the quiz better?
Yes. They're so cute.
All right.
And
So
Ryan's weird dance.
I don't know what you're talking about. First quiz question. What keeps the water in a drop from falling down from the faucet immediately?
Well, you used two terms, so I'm going to say both of them.
Okay.
A hydrogen bond and surface tension.
Okay. Can you tell me anything else about either of those?
Yes. So water molecules, the hydrogen parts have a slightly negative charge. Dang it. Positive charge is a 50-50 there.
Yep.
And the oxygen has a slightly negative charge. And so they want to stay together more than they want to be apart because of those charges. And that those charges are stronger than gravity until a certain point, when there's just a few of them, or like not as many.
Yeah, that's great. And that actually answers the second question, which was why do water molecules stick to each other? And you already went into that with hydrogen bonds. I'm so impressed. Nice job. Third question, why do we see cohesion on the surface of a water drop the most?
Because on the surface, they are not being, is it being pulled? Is that what we would say? Pulled when we talk about them sticking together? They're not being
attracted,
pulled or like attracting in all directions because there's no additional water molecules higher than the surface. And so they're only being pulled or attracting inward towards the center of the water droplet.
Exactly. Yep. And we can see an even better example of this if you watch video from like the International Space Station. And if you've ever seen liquid or water, it's actually a sphere all the way around.
Oh, yeah. I think I've seen that.
Yeah, because it's all attracting inward because there is no gravity to pull it in a downward direction. Well, no gravity. Technically, there is still like 90% of the gravity up there, but that's a whole other issue. But it effectively appears as if there's no gravity. How about that?
That's really cool.
Yeah. Okay, last question. What other factors influence the size that a drop can get before it falls, other than that surface tension and cohesion?
The material that the faucet is made of.
Okay.
Because water sticks to some materials more than others. And also if there's there are other things in the water, but it depends on what those other things are for how it would affect the water molecules wanting to stick together, which is kind of gross to think about, but I'll try to be okay with it.
It's actually fine. It's actually better for you because if you were to just drink pure water and that's all you ever drank, it would actually kill you.
Are you serious?
Yep.
That's not what marketing companies want you to think when they sell you water, though.
Nope.
Interesting. Okay. Sounds like another podcast for another day.
It does.
The other thing I was thinking about is like even like maybe the angle that the faucet is at probably has an impact on it as well, because some of them point like all the way straight down and some of them are more like not maybe a 45-degree angle, but somewhat of an angle and not just straight down. So I would imagine that has an impact on it too.
Yeah, absolutely. Those are all great things. And you gave some great answers today. Congratulations on passing your quiz.
Yay!
That's all the time that we have for today's lesson, though. So why don't you pack up your stuff and get ready for my closing remarks. You can follow us on Instagram and Facebook at I Slept Through Science or on Twitter at Slept Science.
If you have dumb science questions like I do, please send them to us. You can email us at isleptthroughscience@gmail.com, or you can even send us a voice memo and we'll play it on the podcast.
Please rate and review our podcast to tell other people what you think about it, subscribe to make sure you don't miss an episode, and share about our podcast on social media.
Thank you to Beth Reed Miller for the artwork. You can check out more of Beth's artwork at Beth Is Something. Okay, great. Thanks. Bye.
The bell doesn't dismiss you. I dismiss you.